Here's an example of why Newton absolutely had to invent calculus. We have a cylinder, which in real life is a figure skater, 1.7 meters tall and 0.36 meters in diameter, moving on frictionless ice. How that is possible, I don't know, but they're just making it easier for us. So his motion starts at 4 meters per second, and 2 seconds later they want us to figure out his velocity. So obviously he's going to be slowing down because of air drag. The problem is air drag is not only not constant, but it actually depends on his velocity. So here's your calculus here. You have to encounter a force that is dependent on density of air, or fluid, in this case it's air, area, cross-sectional area, for us again it's a cylinder, so we're looking at a rectangle, then the aerodynamic constant, when a cylinder moving through the fluid sideways, not, in other words, not like this, but as a rectangle, not a circle, but a rectangle in the cross-sectional area, then C is 1.1. It's a coefficient, so it doesn't have any units of measure. And then finally, it depends on V squared. V changes, and as V changes, so does drag. And as drag changes, so does acceleration. So everything is changing. Yay! That's why we need calculus. What is it that we're going to do? We're going to remember acceleration on the one hand is our force net divided by mass. This is just a general formula, or we know that formula for force, net force, can be also m times dv dt. Because it's frictionless and the only thing that is affecting our wonderful figure skater is drag, we're going to write 1 over 2m, so dividing by m to get to acceleration, rho a c v squared should be equal to dv dt. And then we're doing a trick that you will see a lot in AP Physics C, but we're going to separate our dv and dt. And how we're going to separate it, we're just going to flip this, put dv v squared, and everything else is on the other side. 1 over 2m rho a c, and our lovely dt. Boom. And now that we have our 2 dv and dt, our 2 d's separated, we're going to integrate. So think about it this way. We're going through to integrate all the velocities from v0 to v that we need to find. And we're going to integrate all the time that from t initial, which was 0, to that t final at which we have this velocity. Let's look at the left. We're integrating v squared, like v to the negative 2 dv from v0 to v. Since this is negative 2, when we integrate, this is going to be negative 1 over v, and then plus, because it's negative over negative, minus over minus, 1 over v0. So this is our left side. What do we have on the right? On the right, we just have all that contraption, 1, 2m rho ac times t. So technically it's from 0 to t. I mean, what's the point of multiplying everything by 0? It's just 0. So let's put it all together. Minus 1 over v plus 1 over v0 equals 1 over 2m rho a c t. Ba-boom! We're after this beauty. So I'm going to juggle this a little bit. I'm going to have 1 over v equals 1 over v0 minus 1 over 2m rho a c t. Then acceleration is forward, then velocity is backward. Or you can say velocity is forward, the acceleration is backwards. So since I treated this as a positive acceleration, I have to make my initial velocity negative. So hence we're going to end up with everything to the negative power of 1. This will be 1 over negative 4 minus 1 over 2 times 60 times a rho for air is 1.2. Area is 1.7 times 0.36. That's his height times his width. Skinny dude. And then 1.1 as a cylinder traveling with its cross-sectional area facing the drag. And then the time is 2. I'm going to get 2 out of there. I'm going to grab my calc. So V is negative 3.8 meters per second, which makes sense because drag slowed us down. So that is a most beautiful example of calculus used in physics.